So, what are the important points? First, I have mentioned the word causal systems, and that if you have a transfer function like this for any system, then the order of numerator should be less than denominator for system to be causal. But as I went more and more into my lectures, I found that I did not formally introduce the meaning of causal and why that's the case, that m should be less than n. So here I added it for you. First, what is a causal system? A causal system is a system where the output at any time point only depends on the current input and previous inputs. It cannot depend on the future inputs, okay? So in any physical system that you see in the real world, the system will not wait until future values come and then it produces a current output. It's not going to happen, right? Any system at this point that gives you an output, it is based on the inputs that it has received so far and it is receiving at the moment. It cannot do anything based on the future because the system does not even know what it might receive in the future. So it's the cause and effect. Cause is the input and effect is the output. Without having the cause, there will be no effect. So that's why we call this system causal. Now, how does that affect the transfer function? Well, let's see. So here I give you an example of a system where the transfer function does not have anything in the denominator. It's only everything in the numerator, right? So if you look at this together, the first example is gs is equal to s plus 1, or we can write it as, of course, s plus 1 over 1. So here the order of denominator, the polynomial denominator n, is 0, and the order of numerator polynomial m is 1. So here m is bigger than n instead of less than n. Well, let's see what happens. So if I call the output y and input u, if I cross multiply and write the corresponding time domain dpq, then here, if you cross multiply this, what would you get? You get y is equal to u plus s times u. And u is this, y is this, and s, s in the frequency or s domain means what in the time domain? Means derivative. So in the time domain, the output u, y, is what? The input u plus time derivative of u, right? Well, what's wrong with that? So all the computers, everything we have, they're all digital, right? They are not continuous. They are not analog, they're all digital. So if I convert that equation into the digital version of it, right? What happens? So I say y at any time point t is equal to u at any time point plus u dot at any time point. But the fact is, u dot, which is created out of u, when you have u at specific time points given to you, how would you get u dot, right? So here is my system where this is g, and this is u, and this is y. And all I have is u at a specific time points, okay? So at time 0, I have one value of u, then at time 0.01, 1, at 0.02, 0.03, 0.04, right? So I have this discrete values of u at each time point. Now, if this is u versus time, the question is, how would u dot versus time look like? How do I find it? Because if it's a continuous curve and I have infinite resolution, I have infinite number of points, well, yes, I find the slope. But what if this function is not given and it's not analog, it's just a bunch of points, discrete? How would you find derivatives? Well, probably what you learn in your courses is a method called finite difference. In the finite difference, what you do is you replace the derivative with its approximation, and the approximation could be forward, backward, or central difference. Here we use the forward difference, And if we do, by the way, it doesn't matter which method you use. I can show you. But if you use the forward difference for u dots, it's going to be u of t plus delta t minus u of t divided by delta t, when delta t is, of course, a small number, the sample time, what we call it. So if I do that and then now cross multiply both sides by delta t and rearrange this discrete version, so this is the discrete version of the ODE. Okay, this is the continuous ODE, this is the discrete, we call it discretize. If we discretize the ODE to get this and then cross multiply with delta t and simplify, that's what you get. So now the question is, what's wrong with this? It says, look, y, the output at any point, is a number, because delta t is a fixed number, it's a sampling time. It depends on the device, the system. So this is a fixed number. It's equal to a number times the current input plus another number times what? Look, this is the future input, t plus delta t, sometime in the future. So your current output depends on the future input. But I said a system is causal when the output does not depend on the future input, but this one does. So what can I say about this transfer function? Yes, I can say this transfer function is not causal. And what was specific about this transfer function? Yes, the order of numerator polynomial was bigger than denominator, okay? Now, on the other hand, if I use another transfer function where the order of numerator here is 0 and here is 1, right? And n here is bigger than m, as we always say. Now, if we do that, rearrange, here u will be y dot plus y, and if we use, again, a forward difference for y dots that you can see and rearrange it, this is the discretized version of that ODE. Now look at this. Anything wrong with this one? This one says the future output depends on the current output and what? The current input. And there is nothing wrong with that. Right? Because the future output depends on the current input, not vice versa. The current output depends on future input. That's not going to happen in real life. But yes, of course, the future output depends on the current input and the current output or the current state of the system. So this is fine. This is completely meaningful in a real physical system. So this is a causal system, and so in general, whenever the transfer function is a polynomial, m order m in numerator and order n in denominator, if we want the system to be a physical system, a causal system, that the input causes the output, the current and previous, not the future, then we should always have m less than n. So hopefully, if I haven't clarified this in my previous lectures, now you see what's going on. A couple of other things that I needed to clarify. So here, in especially chapter 7, we learn a bunch of different plots, including Bode plot, Nyquist plots, Nichols plot, and so on. Right? So if we consider a unity feedback system where the feedback transfer function is 1, so that's why we call unity feedback, correct? We know this Bode plot, Nyquist plot, and Nichols plot, they can be drawn for any transfer function you can imagine. All you need is, in any arbitrary transfer function, I'm not going to call it G or H, I just call it something general, like W of S. All you need is to plug in for S, J, omega, and then either plot magnitude and phase versus omega, they plot them versus each other, or you do the polar plot, right? So these plots can be drawn for any transfer function, including what? Including the Open loop transfer function, in this case, what is our open loop transfer function? If you remember, open loop was G times H. So my open loop transfer function in this case is what? G times H, but since H is 1, it is equal to what? G. So I can plot it for G, all of these different plots, I can draw them for G. I can also draw them for what? For the closed loop transfer function, which in this case is C over R, and it is G over 1 plus GH, and H is 1, so I can also plot it for this transfer function, G over 1 plus GH. So I can plot it for each one of them. Now the question is, which one do we use for analysis when we do, for example, a static error constants, right? KV, KP, KA. When we want to find the type of the system, when we want to find the phase margin, gain margin, and their associated frequencies. We plot Bode, Nyquist, or Nichols for which one? Do we plot it for G and look at the results, or do we plot it for C over R, which is G over 1 plus G? For which one of these, open loop or closed loop, do we do the plots, and then from those we acquire these numbers? Which one? So this is very, very important. Look, if we want to do the Nyquist stability criterion, if you remember, Nyquist stability was what? The fact that your Nyquist of the Nyquist path, right? The projection of the Nyquist path in the GH plane, if that encircles the critical point of -1 and 0. So what transfer function did you use here in this analysis? If you remember, we used what? We used the GH, we used the open loop. So if we want to determine whether a system is stable or not using the Nyquist stability criterion, what transfer function are we going to use? Open loop, not the closed loop. We're gonna plot it for open loop. In this case, G times H, and H is 1, so it's just G. What about the static error constant values? Again, KP, KA, and KV, and the system type, right? What do we do? This is this part of our lecture. If you remember, that we determine the type of the system, and we determined KP, KA, and KV. Remember here? So we said if the slope in the beginning is flat, that gives us 20 log of KP, and it means system is type 0. If in the beginning, on the left side, the slope is -20 decibels per decade, that means system is type 1. And then basically the intersection of the this line and the vertical line from ω1, that gives you 20 log of KV, or the intersection of that with the horizontal ω1 is also KV. And then we learn if it's for -40 decibel per decade, that's a system type 2. And then if you continue it all the way to the place that it intersects the horizontal axis, the intersection point is basically square root of the intersection point, I'm sorry, is equal to square root of Ka, right? So what did we use to find Ka, Kv, or Kp? What is it that we used? If you look, again, for a unity feedback system, what transfer function did we use? Yes, we used G, we used the open loop one, because, or G times H, because H is 1. So we never used C over R in this analysis. We used what? Open loop. So I summarize that for you here so that you never get confused. If I want to find those values, I have to use that, look at the open loop. And system type, or K, again, that means Kp, Kv, and Ka. And the system type N, right? The number of poles at 0. The Nyquist stability criterion, which was if you encircle this point or not in a clockwise manner. And finally, the margins, gain margin, phase margin, and the crossover frequencies. If you look, we also used the open loop transfer function. Look at them. So when we talked about gain margin and phase margin and relative stability, what did we use? G of j omega, okay? So again, we use the open loop. So for any of these metrics and methods, you should use Bode plot, Nyquist plot, or Nichols plot of the open loop transfer function. Now you might say, okay, where do I use the closed loop transfer function plots to get what? Well, I tell you. One of them was the resonance frequency and the peak value, okay, which were here. Here. So when you plot, let me show you in a Bode plot. Here, that's a Bode plot. This is Bode plot of what? If I have, again, that open loop transfer function here, the unity feedback control system here. So this is G, this is R, and this is C. This is the Bode plot for which one? Is that G of j omega that I'm plotting here versus omega? Or is that C over R of j omega versus omega? Which one is that? The answer is it is the closed loop one. So whenever you want to see if there is a peak, if there is a resonance happening, at what frequency it is happening, and how much is the peak value, you have to look at the closed loop transfer function, okay? So make sure that you know which one to use for what. So I mentioned that for you here, resonance. What else you might imagine? The same thing for cutoff frequency and bandwidth. Okay, when you want to look at the cutoff frequency and bandwidth, which we did here, so this is again a Bode plot, right? This is the magnitude part of the Bode plot. What? It's Bode plot of what? Again, this is the Bode plot of, you can see it here. It says the magnitude of what? Closed loop transfer function is 3 decibels below its beginning point. So this is for C over R of j omega. Okay, this is the Bode plot for closed loop. So cutoff frequency and bandwidth, we need the closed loop. And the last thing we had in one of your homework problems, I guess it's the first problem, and an input is given, so this R is given, it's like, for example, 2 sine of t. And G of S is also given, and then it says, what is C of S? Not C of S, C of t actually. If R of t is given, it says, what is C of t? Well, how would you do that? If you remember, we said that if the input has some magnitude, right, and is harmonic, then the output will have a modified magnitude, harmonic with the same frequency and with a modified phase, correct? This is where we had in one of our very first slides. Here. You see? So if I give you x of t, and I ask you for y of t, and look, x is input to the whole system, and this is the output to the whole system. So this guy here is the closed loop transfer function. And I use that with that one and with the input, then I can determine what? The output. Okay, so if I want to use this formula here, which you have to use for problem 1 in your homework, this m and this phi are magnitude and phase of the transfer function, but this transfer function, if you look, we call it G, but don't be misled by G, because G can refer to anything arbitrary. If you don't like it, I can change this, but just know that I would use the magnitude and phase of a closed loop transfer function. So again, if you might by any chance be confused, I am willing to change this G to something else. Maybe I call it W of S or something. As long as I'm sure that you are not confused, I'm happy. So here, let's just change it to make sure that nobody's confused here. Okay, so I do it like that. So that's another place that you should definitely keep in mind. Now, so I mentioned all of that. Finally, you might say, what about these formulas that you said that as omega goes to zero, to infinity, as omega goes to infinity, the slope of the magnitude curve in the Bode plot goes to n minus m times negative 20 decibels per decade, and the phase would converge to n minus n times negative 90 degrees. Okay? This is Bode plot of which transfer function? Open loop or closed loop? And the answer is, if the system is unity feedback, if H is 1, then the order of closed loop and open loop are the same. For example, if this guy is a second order, if this is something like 1 over s squared plus s, this is a second order transfer function, then if I plug that into this formula and find the closed loop transfer function, this is also going to be a second order. This is going to be 1 over s squared plus s plus 1. So it's not the same as that, but the order is the same. And m and n, the difference between numerator and denominator is the same. Nothing is going to change. So which of the Bode plot can I use? The one for the closed loop or the one for the open loop? And the answer is, it doesn't matter. Only for this specific case. Only for this specific case that I mentioned, for this one it does not matter, and the only reason is H does not play any role. H is 1. But if H is not 1, then the order of closed loop and open loop are absolutely different. Okay, so we keep everything in our class for the moment for unity feedback. So these are the very important things that I wanted to talk to you. Make sure you're not confused about them and you have a good grasp of them before I start this short lecture on closed loop frequency response. And this is also related to these points that I just mentioned. So now let's talk about why we need this new topic. So we saw that, well, I learned if I want to find, let's say, a frequency at which, for example, the phase of the system is, the phase of the open loop transfer function is negative 180, or the gain is 0 decibel or so. Well, I do it for the open loop transfer function G, and we practice on that. But now, maybe I ask you a question like this. Let me show you the question, then we go back. So the question here says that I have a unity transfer function, a unity feedback system, and the G is given to me. So the G is a transfer function like K over S times 1 plus S. Now, I want you to tell me how much of K I should use in this system so that the peak value for the resonance, MR, is 1.4 units. So how much is K such that the peak of the resonance is 1.4? Or maybe they say maybe the resonance frequency is 2 hertz or 5 hertz or what? How do I do that? Well, if it says find K such that the gain margin is so much or the phase margin is so much, well, that wasn't a big deal because I would plot the Bode plot of G, the open loop transfer function, and based on that Bode plot, I could find, and based on the gain or phase margin, I can find K. But here it is asking about the peak value of the resonance, which is a property of not G, but it is a property of what? If I call this C and R, it is a property of C over R, which is G over 1 plus G times H, which is 1. So the magnitude of this transfer function, versus omega should be plotted for the Bode plot. And the question is, okay, fine, let's say I can do that, maybe. Then how do I find the locus for this constant magnitude? How do I do that and then intersect them and then find which frequency and how much the K is? Right? So far, I have not found any loci in the polar plot, like a Nyquist plot that, or a Nichols plot that you can see here. This is a Nichols plot. I have not seen how the constant magnitude of the closed loop transfer function would look like for different values of MR. How does it look like in a Nichols plot or Bode plot and so on? So that's important to know how they did look like so that we can draw them and then intersect G or 1, G over 1 plus G, and then see the behavior. So this is what we do. So this is how we approach this problem. We say, well, again, assuming that the system is unity feedback, the closed loop is G over 1 plus G, and now I assume that G, the open loop, is in general a complex number like x plus j times y, where x and y are, of course, both functions of what? They are both functions of omega. And the closed loop transfer function, C over R, I write it as m times e to the j alpha, where m is magnitude of the closed loop transfer function and alpha is the phase of it. Again, here, m is a function of omega and alpha is a function of omega. The question is, what relation exists between x and y and m and alpha? If I give you x and y, how would you give me back m and alpha? How do you do this mapping? Well, of course, we use this formula, the relation between C over R, which is this guy, and G, which is this one. So if you do a little bit of simplification, you find the relation between X, M, and Y, which is this one here that I showed on the top line. This is for the case that M is not equal to 1. And for the special case that M is equal to 1, that will be simplified to a vertical line at X equal -1/2. But for the case that m is not equal to 1, let's say 1.4, like this example, then what type of curve is this? Well, of course, you know from geometry that that's the equation for a circle centered at x equal -m squared over m squared minus 1, y of 0, and the radius of absolute value of m over m squared minus 1, right? So, what does that mean? That means if in the xy plane, which is basically the Nyquist plot of g of j omega, and g, remember, it was the open loop transfer function. So like what I learned in the past, I only do what? The open loop transfer function Nyquist plot, not the closed loop. I draw the Nyquist plot for the open loop, just like what I did in the past. I do it for g of j omega, which has x as real axis and y as imaginary axis here that you can see. If I do that, which you can see it over here in this example, or let's go back actually to this case because it's kind of different than this one. But if I do it somehow and I find that, well, maybe the Nyquist plot for that case is, you know what, let me actually do it in MATLAB right now. Why should we imagine? Let's do it. So it is s over s plus 1. So we say system is transfer function of, and I do it for k of 1. So this is 1, and the denominator is s times s plus 1, 1, 1, and 0. So I say Nyquist of system. Yes. Okay, so this is the Nyquist of that system, right? This is the Nyquist. Of course, we only look at the bottom one. We know the top one is for negative frequency, but this is the Nyquist for that system. Now, can I, on the top of this, show what m of 1.4, as this problem asks, would look like? Can I do that? If I do, then all I need is the intersection of them, or the way that I adjust k to make them reach each other, right? If I can do it, then life will be easy. So instead of me redrawing the Nyquist plot for the closed loop based on this formula, I draw the Nyquist of the open loop, like what I just showed you in MATLAB. I draw the Nyquist of that, or the Nichols of that, or the Bodhi of that. Now the question is, good, fine. I did that. Now I want this magnitude m to be a constant number, like 1.4. Well, how does it look like in a plane formed by real and imaginary part of G? How does it look like? And the answer is, it looks like a circle. And these are those circles that you see. So these are the loci of what? Magnitude constant for the closed loop transfer function for different m values. You see, they are all circles with different radii, different centers, and this is just for the special case of m equal 1, and of course this point here is negative 1/2. So now if I have this on the top of that Nyquist plot that you saw, that Nyquist plot was plotted for k equal 1. And I want this curve to intersect what m value? M of 1.4, which is this one. You see right now, this is m of 1.4, and this is the Nyquist of G. They are not going to intersect each other. This curve and that one are not going to intersect each other. There is no intersection. But I know if I change k in the Nyquist plot, the Nyquist would change. Okay, the location of that would change, and I can bring this k bigger and bigger until finally these two guys would touch each other, and that will give me the k that I need, right? That will give me the k which makes m equal to 1.4. So that's the whole idea of this. And the question is, can I plot all of the circles like here in MATLAB 2? And the answer is yes. All you need to do, and I mentioned that here for you in this example, all you need is for a Nyquist or a Nichols plot, just say grid on. As simple as that. Just say grid on. It's not like a Bodhi plot that turns on the vertical and horizontal grid lines. This is different. Look, again, this is the Nyquist of the system with k equal 1, right? Now, this is what I do. I just say grid on. Look what happens. Let's see if it allows me to zoom out. I don't know if it allows, but even if it doesn't, you can see here, look. These are different MR values. These are those circles, of course, a portion of them, because this Nyquist is special, so it's just showing on one side of the frequency axis. But that is interesting that for this case, these are the MR value, these are the portions, and if you can see them here, these are circles, of course, but the aspect ratio is quite weird. This is 1 unit, this is 40 units. So these are the parts of these circles. These are like these guys here. If I go back, it's this area. Zoom. That's this area here that I'm looking, and then these numbers are converted into decibels. So for example, if we go back again here, you see it says what, 6 decibel, right? Or 2 decibel or something for that matter. So what does it mean? Like 10 decibel. So what do you think 10 decibel is, or 6 decibel is? If you remember, when I want to convert a decibel back to a normal unit, I divide it by 20 and raise 10 to the power of that. So 6 decibels means 10 to the power of 6 divided by 20. And that is 1.995. So 6 decibel is almost like MR equal to 2 units, right? So if I have MR equal to 2 units, which is this guy here, this one, this MR equal 2, this corresponds to what? 6 decibel. Okay? And the higher I go, the decibels would drop, and the lower I go, the decibels will go up, right? Because it's 6 times like 10 of that number. So the bigger the number is, the bigger the like 10 is, and the bigger the 20 times that is. Correct? So MR of 2 is roughly 6 decibel. And again, you can see it here too, right? So you see, as I go up, the decibel drops. As I go down, the decibel goes up, or the MR goes up. So you can do it here, but Nyquist, for answering these problems, Nyquist is not typically the easiest type of plot if you want to solve these problems relating to resonant values. Nyquist is a little hard. What you typically rather do is either a Bode plot, or better than Bode plot in this case for this type of problem, I always recommend you use Nichols plots, because you can see gain and phase all together in one plot. And the best thing about Nichols plot is, if you change K, what happens to the Nichols plots? Or even Bode plot, what happens to them? Let me tell you very fast here. So if I have G1 equal 1 over S times S plus 1, and I have G2 equals 3 times S plus 1, what's the difference between the Bode plot of these two systems, where they only differ in different in a gain, right? 1 or 3. So if you look, the magnitude of G1 is what in general? It's 1 over, of course, omega times the square root of 1 plus omega squared. The magnitude of G2 is 3 over the same thing. And what about the phase? The phase of G1 is the phase of numerator, which is 0, so it's negative arctangent of omega, negative arctangent of which is omega over 0, so it's negative 90 degrees. And G2, if you do, you're going to see that's the same thing. So if you multiply a transfer function by a constant number, the phase is not going to change, only the magnitude is different, right? Even if you take 20 log of that, it's going to be 20 log of 1 versus 20 log of 3, right? So what does it mean in the terms of Bode plots? So if I have, for example, this is a magnitude versus omega, if this is, let's say, the magnitude of G1 times 20 log, of course, how does 20 log of G2 would look like? It exactly look like this, except since this magnitude is a little bigger, it's going to be shifted up. It's going to be exactly the same shape, the same everything, except you just shift it up. So this is going to be 20 log of G2. And how much is this vertical shift? It is going to be 20 log of this constant over the other constant. These many decibels. Okay, so in magnitude plots, the best thing is changing a constant in the numerator means shifting it up and down, and that's what you see in this figure here. That's exactly what you see here, that here the magnitude is plotted, of course, instead of plotting versus omega, it is plotted versus phase. And I tell you why this is better than Bode plot. And you see that this solid one is the g of s for k equal 1, while the dash one is g of s for a k other than 1. And you see the difference between these two is simply a vertical shift. How much is the vertical shift? 20 log of the gain in this one, which is k, compared to the gain in this one, where k was equal to 1. So the shift is simply 20 log of k, right? So that's the difference between these two. Now, how does the loci of mr equal 1.4 would look like in a Nichols plot? I just showed you that in a Nyquist plot, so this is a Nyquist plot. In a Nyquist plot, the loci for different m's, they look like these circles. And also, by the way, we don't really use it in this course, but I can also show you that the loci for a constant phase of the closed loop transfer function based on the open loop one would also look like circles, but the circles are vertically aligned instead of the magnitude circles, which are horizontally aligned. Okay, as I said, we mostly use this guy in our course. We barely use this one ever because we're mostly concerned about the magnitudes. Now, how does those constant m values and constant alpha values, these circles, how do they look like in a Bode plot or in a Nichols plot? Well, in a Bode plot, a constant magnitude loci will look like this curve. And a constant phase would look like this curve. So now what do you need? You need to basically have your original G with k of 1 and then cut it with this one and then shift it up and cut it again, okay? And you have to make sure it is just cutting at one point, so it has to be tangent to it. And the same here if it's needed. While in Nichols plot, where you plot G directly magnitude of it versus what? Angle of it, instead of both of them separately versus omega. In Nichols plot, the constant m's and the constant alphas look like this complicated shape here. So some of them would look like ellipses with different decibels, and this also, these other curves here are for different angles of alpha. So this is a complicated grid, but it is easier to make a curve tangent to these circles or ellipses of constant m versus doing it in the Bode plot. So we always choose this shape versus this one whenever we want to solve that kind of problem. And we don't do it here. Again, why don't we do it here? one more time, because in either of these two curves, either this top one or the Nyquist, if I change my gain from one number to the other, so if this is k of 1, if I make k to 3, it just shifts up. And the same here, if in the Nyquist plot it looks like this, for example, if I change it, so this is for k of 1, if I change it to k of 4, again, it's going to be simply shifted up. Okay, so in both of these plots, a simple change in k means a shift up and down, but not in the Nyquist plot. Here, if I have a curve for k of 1, if I want to do it for k of 4, it's not going to be a simple shift up and down, and I can show you in MATLAB. So since in Nyquist the stuff are more complicated, nothing is in decibels, the major reason everything becomes shift up and down is because the logarithm and converting product and powers into multiplications. That's why here nothing is decibels, everything is a polar plot. So we don't really use Nyquist, and again, because the shape in the body is not as good and pleasant, we typically use a Nyquist plot like this. So in this problem, what do we say? We draw the loci for MR of 1.4. If you go back here, we can see 1.4 means how many decibels. We can just do it, right? So we say 20 log 10 of 1.4 is 2.92, right? So if I can find somewhere here that is 2.92 decibel, that is the same as 1.4, so 2.9 decibel, it's close to 3, right? Okay, so it's here, close to here. That's kind of the curve that I need. And that's what you see here. That is the curve. This is the transfer function Nyquist plot for k of 1. Now I say, well, how much should I shift this up so that it becomes tangent to that curve, okay? It has a solution at one frequency only. And if you do these two plots, you can find out all I need to shift this up is about 4 decibels, right? If you look at this value here, this is 4 decibels. If I shift this up 4 decibels, then they're going to be tangent. And that 4 decibel is this 20 log k of vertical shift that would happen for changing k from 1 to arbitrary k. So now if I solve this, I'm going to see that the k I need is 1.59. Okay, so that's how much of gain that I need to make this much of peak magnitude happening. And again, you might wonder, well, can I do this in MATLAB? Yes, because drawing this loci by hand is not really easy, but MATLAB does it for you. In a Nyquist plot or in a Nyquist plot, all you need to do to add these locus is simply say grid on. So now, let me show you that very fast in Nyquist. So we defined this transfer function. Now I say, what is the Nyquist of the system? And that is the Nyquist. And then to add that loci on the top of it, all I say is, hey, grid on. And grid here means constant M circles or M loci. And look at that. It added all those shapes for me. And now I'm looking for a value of what? 20 log 10 of 1.4, which was around 3 decibels, right? So I am, if I zoom in here, I am looking for a curve almost close to 3 decibel. And all I need is to shift this blue curve up this much to make it tangent. And if you, again, look at this from our curve, you see that is almost 4 decibel. So this is how you do it in MATLAB. By the way, you're just approximating. It's not 100% accurate. But now, if I can do on the top of that, I define another system where this guy is 1.59. Okay, and then I say, I don't know if it does hold on or not, but I'll try it. And then say do the Nicole of this one too. Yes, it does. And now this one is in red. You clearly see it is shifted. And now if you see, it is almost tangent to the 2.9. So this is 3. This one is 2, between 2 and 3. This is very close to 3, so that is almost tangent to loci of 2.9, this red one. So hopefully I could tell you about this problem of closed loop frequency response of unity feedback systems. And again, the main reason we do it, because some of the problems are not asking for a gain margin or a phase margin. They are asking for a value of a resonance peak or a resonance frequency or so, and or cutoff frequency or bandwidth. And for those problems, I need the closed loop transfer function. Okay, so we'll continue next lecture. Thanks.